Independent events. Great. This is super important. Two events, A and B, are said to be independent if the chance that A occurs, given that B has occurred, is the same as the chance of A. That is, given this new information that B has occurred, it doesn't change the chance that A occurs. Okay? Like, for example, given that, I studied 1,000 hours for an exam, what's the chance that I do well on the exam? It's probably pretty good, right? But otherwise, if I just pick a student at random who may or may not, study 1,000 hours, then the chance of that student doing well on the exam may be different, right? So the idea here is that maybe studying will actually help your exam score. You can think about that. All right. So another way to write this, it turns out, these three statements are actually equivalent, meaning that if one, then all of them. Okay. But it turns out that if A and B are independent, then B and A are independent. It works that way. Okay. Given that A has occurred, the chance of B is the same as it was. It's the same as the chance of B, okay, if A and B are independent. Also, it turns out if A and B are independent, you can write the chance of both of them occurring as the product of the two probabilities. So these are really probably, I think, these are the best way to define independence. Okay. This, some books use it to define independence. It turns out it's perfectly okay. This is equivalent to these two statements, but this is just, I think, this is more useful. This is useful in computing probabilities. Okay. And if you know that two events are independent, then the chance that both of them occur is just the product of the two. Now, before we do some examples, it's important to note that independence and disjointness are they are not the same. Independence and disjointness are not the same. Not the same. Look, here's a picture of disjointness. Disjoint events. Look like this, right? Here's A, here's B. They do not overlap. They don't intersect. This is what disjointness looks like. Okay? What does independence look like? Well, some might say it looks sort of like this. No, just kidding. But actually, it looks kind of like that. It looks kind of like that. Here's a good picture of independence, and I'm going to make use of this black line here. Let's say, here's the event. Let's say all of this is the event A. Okay. All of that. And let's say all of this is the event B. Okay. Now, you can see that my sample space is this blue square. It's everything inside the blue square. And inside the blue square, I sort of have four regions, right? I've got this little rectangle up here, this rectangle up here, the rectangle down in the lower right, and the rectangle down in the lower left. All of this lower left rectangle is in A. This all the points up here in the upper left rectangle are in both A and B. Get it? Makes sense? Okay. So here's the idea. A and B are independent. This is a picture of what independence looks like. They must, in fact, necessarily overlap. A and B must overlap for them to be independent. And so the deal is that given that B has occurred, the chance of A occurring is the same as it ever was. Okay? You see, the probability of A occurring, you can write that as it's sort of it's the probability of A given the sample space, right? given that, but you know, this holds by axiom 2, so we never actually write this because it's always given that something in the sample space has occurred. But you know, if I want to, I could write it like that, and then using the definition of conditional probability, I can write it like this, right? So the probability of A can be viewed as this region right here, yeah, divided by 1, divided by the total. So now if I come along and I say, hey, guess what? B has occurred. And then you say, oh, okay, I can get rid of all this other stuff. Now, given that B has occurred, what is the probability that A has occurred? Given that B has occurred, what is the chance of A? Well, it looks like it's actually the same as it ever was, because you know what? It looks to me like A sort of takes up about 2/5, right? The chance of A occurring in this example looks to be about 2/5, right? Now, given that B has occurred, and maybe B takes up about 1/3 of that region up there. Okay, so it looks like, though, you know, given that B occurs, the chance of A occurring is still 2 parts in 1, 2, 3, 4, 5, right? It's the same because A seems to take up proportionally just the same amount of B as it does for the entire sample space. And sure enough, if I work this out and use the formula for conditional probability here, then this looks like this, right? Chance of A and B is this looks like 2 parts out of 15. 2 out of 15. What's the chance of B occurring here? It looks like 5 parts in 15. Okay, 15's cancel and it's 2/5. Okay, so that's the idea. That's the idea. Note that if 2 events are independent, they must in fact overlap. But if two events are disjoint, they do not overlap. So in fact, if A and B are disjoint, then they are highly dependent, meaning they're not independent. Because hey, look, in this case, what's the probability of A given that B has occurred? It's 0, big fat 0. Okay? Maybe the original chance of A was 50%, but now if I tell you that B has occurred, it drastically changes the chance of A occurring. A cannot occur if B occurs in this case. Make sense? Okay. So that was that statement right there. Okay. Let's take a look at this example. Are the events white die shows a 2 and sum of dice is at most 4 independent? Okay. Well, you can check this out by just comparing, you know, what's the chance that the white die shows a 2? Compare that with the chance that the white die shows a 2 given that the sum is at most 4. Okay? If these two quantities are the same, if this quantity equals this quantity, then they're independent. Okay? The two events are. Now, what's the chance that the white die shows a 2? That turns out to be a 1/6, doesn't it? What's the chance that the white is a 2 given that the sum is less or equal to 4? That is 2/6. Right? I can tell that by looking at the picture. The chance that the white die is a 2, by white I mean black, right? 1/6. Right? 6 out of 36. Okay. But the chance, given that the sum is less or equal to 4, here are all my sums that are less or equal to 4, given that, the chance that the white die is a 2 is 2 out of 6, 2 out of 6, or 1/3. Okay, 1/3. So since these are not equal, so since the probability that the white is 2 is not equal to the probability that the white is 2, given the sum is less or equal to 4, the two events, call them white equals 2 and sum is less or equal to 4, are not independent. Okay? That's what you have to do. You have to compare those quantities. What about white die shows a 3 and the sum of dice is at most 4. Okay, white die shows a 3 and the sum is at most 4. Probability that the white die shows a 3, well, that's also 2/6. What's the chance that the white is a 3 given that the sum is at most 4? Okay, that's you know, I can use the formula here, or just look at the picture. I'll use the formula first because it's harder, I think, for me. Okay, sum is, there we go, 4. Chance that the white is a 3 and the sum is less or equal to 4. What's the chance that the white die is a 3 and the sum is, let's see, there's only one way out of 36 to do this top part, right? What's the chance that the sum is less or equal to 4? 6 out of 36, so that's 1/6, right? So these two events are also not independent. So the event white equals 3 and sum is less or equal to 4 are not independent. Okay. Another way to think about that is that, you know, the chance that whoops, hang on a second here. I made a mistake, didn't I? You know, it's perfectly okay when I make a mistake for you to just raise your hand and let me know so that I don't just keep on going. But that's okay. All right. It's actually a 6th, right? So, whoops, guess what? These are independent. Chance that the white is a 3 is 1/6. But given that the sum is less than or equal to 4, it's still a 6th. Okay, so you can see that if you look at the big picture here, the chance that the white die shows a 3 is, well, there's 6 ways, right? There's the white die showing a 3. It's this row right here. It's the third row. 6 ways out of 36. If I come along and tell you though that the sum is less or equal to 4, guess what? There's one way out of those 6. Okay, so given that extra information that the sum is less or equal to 4, it doesn't change the chance. It doesn't change the chance that the white die shows a 3. Okay. On the other hand, it does change if I tell you that the sum is one of these is 4 or less. That does change the chance that the white die shows a 2, right? That chance actually increases because now you've got 2 ways out of 6 is a third. Okay. So without that extra information, your chance of the white die showing a 2 is only 1 in 6. But with this information, that it's one of these, it actually increases the chance that the white die shows a 2 to 2/3. I'm sorry, to 2/6 or 1/3. Okay. Okay. I'll let you all work on some of these examples from slide 11. But I'll do a couple of them here. Suppose you toss a fair die 4 times, just one die. Then what's the probability that you see 5, 5, 6, and then 1? Well, by independence, you can just multiply the probabilities, okay? And that is, I mean, we'll assume that these die tosses have independent outcomes. So what's the probability that you see 5, and then 6, and then 1? It should be just the chance that you see a 5 times the chance that you see a 5 times the chance that you see a 6 times the chance you see a 1. It's just 1 over 6 to the 4th, which turns out to be 1 divided by 6 to the 4th. About something really small. See that? 7.716 times 10 to the negative 4th. Okay, that's really small. What's the probability that you see 4 even numbers in a row? Okay, 4 even numbers in a row. Well, the chance that you see an even is a half, and then the chance you see another one is a half, and then the chance that you see another one is a half, and the chance you see another one is a half. So that's 1 over 2 to the 4th, or, okay, 0.0625, about 6%. What's the probability that you get a straight? Actually, you know what? I should probably say chance that you see 4 evens, chance that you see 5, 5, 6, and then a 1 in that order. Okay, is that. Now, what's the chance that you get a straight? And by straight, I mean, you know, you see, let's say that you get a 1, 2, 3, 4, or you see a 2, 3, 4, 5, or you see a 3, 4, 5, 6. Okay? And you have to do them in order. Okay? That is, you know, if you see a 1, 2, and then a 4, and then a 3, maybe that's not, maybe we won't count that as a straight. You have to see them in order. Probability that you see a straight. In order. Okay? Well, let's see. Actually, we just counted the number of straights, right? The total number of straights is 3. 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 6, right? Now, how many different possible outcomes are there? 6 to the 4th, right? So that's 3 over 6 to the 4th. Oops, that's not right. 3 over 6 raised to the 4th power is 0.0023148. Approximately. It's pretty small. It's about 20% of a percent. Okay, that's pretty small. What about what's the chance that you see a straight and maybe we allow it to be in different orders? Okay, let me do this one on the back. What's the chance? Can be out of order. So it's sort of like you have several dice. Maybe you have 4 dice and you're going to roll them all at the same time. You want to know what's the chance that you see a 1, 2, 3, and 4 in the pile there. Okay, so again, so this means that you can, 1, 2, 4, 3 counts, a 2, 3, 4, 1 counts, a 4, 3, 2, 1 counts. Can't you do it? Can't you think of it like this? I mean, there are 3 ways to get. We already know from last time that there's certainly 6 to the 4th total number of ways to roll 4 dice, right? Now, I know that there are 3 ways to get a straight, three different sets of numbers that'll get me straights, right? Like 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 6, right? But then for each set of numbers there, how many different ways can you reorder them? 4 factorial. That's right, okay? So if you can follow this, you're a genius. So 3 times 4 factorial, okay, you see that? 72. Divide that by 6 to the 4th. Get 0.05 repeating. 0.05 repeating. About 5 or 6%. Okay? All right. So I'll let you take a look at some of these and try those out. Okay?